Right now, there are roughly 2,000 thunderstorms actively tearing across the planet, and considering humans have been flying kites and balloons into them for nearly 3 centuries, the physics of a lightning bolt should be a closed case. The classical model is straightforward. Inside a storm cloud, tiny ice crystals rub against each other like socks on a carpet. The crystals that lose electrons float to the top, while those with extra electrons pile up at the bottom. These separated charges generate an electric field. When that field reaches 3 million volts per meter, the air comes undone. Electrons are violently ripped from their atoms, triggering a runaway avalanche that we see as a blinding flash of light. In the 1960s and 70s, physicists tested this by shooting small rockets with trailing wires directly into charged clouds, hoping to measure that field at the moment of impact. This chart compares the voltage we need against what we actually find. To force a spark, we need 3 million volts per meter, but measurements inside real superstorms consistently peak at barely a third of that, and typical storms hover around 1/10. The math simply does not work. Based strictly on the known laws of classical physics, a lightning bolt has no way to begin. In 1994, satellites searching for deep space cataclysms detected high-energy gamma rays coming from the clouds below, radiation usually reserved for the final collapse of a dying star. To explain how a cloud could produce star-level radiation, astrophysicist Joseph Dwyer turned to the physics of subatomic particle collisions, proposing a process called a runaway relativistic avalanche. An electron moving near light speed ignores air drag, slamming into an atom to emit a gamma ray. This transforms into an electron and a positron. Pushed backward by the electric field, the positron crashes into another atom, starting a multiplying feedback loop. To see if this was actually happening, a 2023 NASA flight called the Aloft mission flew a high-altitude plane directly over the core of the most ferocious tropical storms in the Gulf of Mexico. They found the clouds were flickering with radiation. These subatomic feedback loops generate enough localized energy to jumpstart the air, compensating for the missing voltage that classical physics couldn't explain. However, this feedback loop requires an initial electron already moving at nearly the speed of light, something a low-voltage cloud is unable to produce on its own. Researchers at Los Alamos National Laboratory recently analyzed radio wave data from lightning strikes in the New Mexico desert to track the exact path the current takes at the moment of initiation. This grid tracks the start of those strikes. If the cloud's electric field were the only force at play, the bolt would follow it vertically. Instead, the data shows a slanting angle, suggesting an outside force is pushing the electrons. That slanted trajectory points to an origin far beyond our atmosphere, a cosmic ray shower. Deep space events like feeding black holes or supernovas expel atomic shrapnel, a lone proton or an iron atom, at nearly the speed of light. These fragments travel billions of light years across the universe and slam into Earth's atmosphere. That collision sprays a jet of high-energy debris down into the cloud layer. These particles have enough momentum to forcibly rip electrons from their atoms, providing the initial high-speed trigger the lightning chain reaction needs. If this holds true, the first spark of a terrestrial storm depends on a dying star billions of light years away. The reality of lightning is a collaboration between ice crystals, subatomic avalanches, and cosmic rays. The precise recipe is still debated. Mapping the exact combination of these forces will require even more sensitive measurements of the gamma rays and radio waves emitted during a strike. This data maps out a storm that operates like a terrestrial particle accelerator, colliding matter and antimatter right over our heads. Every time the sky lights up, you are watching the same violent physics found in the deep cosmos, connecting a rainy day on Earth to the mechanics